Hello everyone, welcome back. So we are going to have a brief review of what we discussed in the last session, right? So I believe we were talking about equilibrium in greater detail, right? So we are talking about how equilibrium is defined by or is driven by thermodynamics. And I believe we are trying to look at how delta G affects a particular reaction reaching equilibrium or not, and we define delta G as delta H minus T delta S, and then we tried to look at into greater detail with respect to change in enthalpy and then change in entropy, right? We then looked at Gibbs energy of mixtures, right? Gibbs energy of system or mixture, and then we calculated delta G value for a reaction, which more or less is the change in Gibbs energy of a system with a small change or infinitesimal change in the reaction, right? And then we calculate that as, let me see if my memory serves me right, Vi mu I of the products minus Vi mu I of the reactants, and then we discuss the relevant aspects or applications, right? But this is the take home message now, right? And Gibbs energy of the system again is what now? Summation of Ni mu I, right? And Ni is the number of moles, mu I is the chemical potential, and nu I guess is what now? The stoichiometric coefficient. So here we are now going to talk about what do we say, the calculation of Gibbs energy or change in Gibbs energy or Gibbs free energy for non-standard conditions, right? So in the previous cases classes we talked about how to calculate it at standard conditions of temperature, pressure and activity of the compound, right? So now let us move on to non-standard conditions and let us first look at what are the aspects we need to consider now. The first aspect is the composition, right? Composition of the system, or you can think of it in layman terms, or the concentrations of the various compounds. So a better term if you delve into it in greater detail would be composition. So there are two aspects. Composition is made up of, or we are going to consider the reactants, reactants, and then the non-reactants. So I guess just for illustration purposes, so let us say I have a beaker or a batch reactor here. I have compound A, B, C, D, E and F at different concentrations, let us say, right. So but my reaction is something like A plus D goes to so on, let us say, right, various products here. So how do reactions take place now when what do we say, the compound A collides with compound D, right? There is a physical collision, that is when in general you have a reaction taking place, yes. So in general the greater the concentration or composition, the greater the concentration of the reactants, the greater the probability for collision. Probability of collision is going to be higher, let us say, and thus the greater the concentration of your reactants, the greater the chances of your reaction going through. So that is one aspect we are going to look at. And the second aspect is obviously the effect of the composition or the effect of the non-reactants in the solution now, right. So now here let us say we are concerned with the reaction A plus D going to products, let us say, right, or A and D colliding or reacting with each other and going to products. But here in the solution we also have C, B, E and F, right. So they either due to their charge, right, in general there will be charge, or some of the compounds or most of the compounds will have a charge, they can affect, right, the interaction between A and D, right, by interfering with either A or D, usually due to charge, right, and there are other aspects but we are not going to go into greater detail. So these interactions, right, or interferences due to the non-reactants will in general tend to hinder your reaction now. So greater the concentration of your non-reactants, that ends up hindering your reaction now. So here we talked about an example again, A plus D going to products, right, or A and D going to products. So they greater the concentration of A, and greater the concentration of, let us say, is going to B plus C, right. And let us say if greater the concentration of A and greater the concentration of D, the higher the chances of collision between the molecules molecules of A and molecules of D, and for the reaction to go through. But let us say if the greater the concentration of other non-reactants such as B, C, E and F, they are going to affect the interactions between A and D, right, and thus you are going to have hindrance to your reaction now. So again, this is generic background that we are going to look at. So obviously composition of your particular system is an issue, and let us see what else we have here. And so we looked at composition, and within composition we looked at two cases: composition of the reactants and composition of the non-reactants. And the second aspect which most people are aware of, I guess, is temperature. The third aspect we considered, I guess, is pressure. Again, if you will remember, how did we look at, or what did we define or try to identify when we talked about the standard conditions now, right. So we said when the activity of a compound is equal to 1 and also temperature equal to 25 degrees centigrade, right, and pressure is equal to 1 bar, we said that the system is at a standard condition, right. So we are just looking at the three aspects when the system deviates from these three standard conditions. So initially we looked at composition, right, and then now we are going to look at temperature. So in general, the greater the temperature, let us say, the greater the chances of collision, the greater the kinetic energy on your system, let us say, greater the temperature, the greater the kinetic energy of your molecules, pardon me, and the greater the chances of collision of one molecule with the other. So in general, again please keep in mind we are talking about generics here, we are going to look at specific cases later on. The greater the temperature, the greater the chances of the reaction going through though, right. So with respect to pressure, greater the pressure for generic cases when let us say there is an increase in volume, let us say, right. If the volume is increasing, think of this now, if the volume is increasing due to a reaction, let us say, 2 moles going to 5 moles or so on now. Initially you had 2 moles and now let us say you have 5 moles. But if you increase the pressure compared to the standard conditions, right, it resists the change in volume. Yes. So what does that mean? So in general, if the pressure is increased, it's not it's not favorable for the reaction, let us say, but we are going to look at that how. So it's going to hinder the reaction, especially when there is a change in volume such that the volume increases of your particular reaction. These are the generic cases and we are going to come back to that into or look at that in greater detail. So there are 3 cases. So first we are going to talk about composition here and reactants or how the composition of the reactants affects your system. So let us move on to that particular aspect. So concentration or activity, right, is what we are going to look at. So composition of reactants here, right. So in general, think of this now, let us say you have what is this now, our generic equation, we have mu A, mu B, B. So stoichiometric coefficients here, mu A, B, C and D, and A, B, C, D, right. So this is our generic reaction. So think of this now, let us say at standard conditions, let us say the system is at standard conditions of temperature, pressure and activity, right, and the reaction has gone through by a small extent, let us say an infinitesimal extent. So now what is going to happen though, the number of moles of your compounds are going to change, right. So what does that mean? Your activity is now no more equal to 1, so right. So then we are now entering the domain of the non-standard conditions, right. So that is what we are going to discuss here. So in general, I guess we denote activity of a compound by the what do we say now, these brackets I guess, and square brackets for concentration now. So activity of a compound by the curved brackets I guess, I am not sure, I am unable to remember what we call them, or activity of compound I, in general when we use the square brackets, we refer to that as the, or we use them to refer to the concentration of a particular compound now, right. So, in general we are going to again look at the chemical potential here, chemical potential of a particular compound. This is at non-standard conditions obviously equal to the mu I naught plus RT natural logarithm of activity of compound A, right, or let us say for sake of writing it down in an easier form, let us say we are going to use a different nomenclature here, natural logarithm of activity of I, of compound A, right. So, we are going to use this and go ahead I guess, and what do we know here I guess, delta G is equal to what now, the change in or summation of mu I ui of the products minus mu I mu I of the reactants, right, and what will that be equal to I guess. So, we can now substitute here for this particular reaction, and so delta G I guess is equal to what now, mu C V C mu C plus mu C D minus mu A minus nu B mu B, right, and this is what we have. So, let us say we substitute for this is at the standard condition or such, let us say, and this is at the non-standard conditions, pardon me, and we know that if it is at standard conditions it is going to be right, this is what we have, this delta G is at the non-standard conditions and this obviously is at the standard conditions. So, right. So, let us try to expand this particular case here and also try to apply what we just have. I guess the background information is mu I at non-standard conditions is obviously equal to mu I naught plus RT natural logarithm of the activity of I for a given, or for the standard conditions of temperature and pressure, which is 25 degrees centigrade and 1 bar. So, let us try to plug them in please, and what am I going to hit here I guess, let us see if I can get that up, okay. So, I guess without troubling you with the minutiae here or minute details, so let me see if I can bypass some of the equations here, right. So, what will that be equal to? That I guess will be equal to V C mu C naught plus nu D mu D naught minus mu A naught minus mu B naught, right, plus V C RT into natural logarithm of activity of compound C plus V C RT, pardon me, not V C now, it is going to be V D RT natural logarithm of activity of D minus V A or mu A, pardon me, RT natural logarithm of activity of A minus stoichiometric coefficient of B RT natural logarithm of activity of B, right. So, and again please note that this particular term or set of variables is nothing but delta G naught, right, and so again here we have natural logarithms here, right, and so we can try to, what do we say, make this particular set of variables more concise, right. So, let us do that in the next slide I guess. So, I guess I am out of space here, so let me erase that here itself. So, now we have delta G is equal to delta G naught, right, plus RT into natural logarithm of activity of C raised to the power of its stoichiometric coefficient into activity of D raised to its stoichiometric coefficient by activity of A raised to its stoichiometric coefficient into activity of B raised to its stoichiometric coefficient, right. And so, this is what we have here. So, delta G at non-standard conditions as in the temperature and pressure are still at 25 degrees centigrade and 1 bar, but the activity is no more equal to 1 of the relevant compounds, and so then we end up getting this particular equation, I guess. So anyway, this is the take home message. You don't need to mug this up in greater detail, I guess, right. So now we are going to move on. So here we have a new term which is called reaction coefficient, I guess. So reaction coefficient, we define that as being equal to the activity of the products raised to the stoichiometric coefficient of the products by activity of the reactants raised to the what do we say now, stoichiometric coefficient of the reactants, which in the earlier case was activity of C raised to the stoichiometric coefficient of C into activity coefficient of D raised to the stoichiometric coefficient of D by activity of the reactants, which in that case were A and B, raised to their respective stoichiometric coefficients, right. So again, thus this is called the reaction coefficient. It's sometimes also called as ion activity product, ion activity product. People use them both as often as each other, right. So here please note that the system can either be at equilibrium or not at equilibrium. So again, if we now rewrite delta G equal to delta G naught plus RT natural logarithm of Q, right. And in this case now we are going to talk about a principle that people might have heard, Le Chatelier's principle. So I guess what does this mean now? It says that if a system at equilibrium, let us say if a system is at equilibrium and it is disturbed or perturbed in any manner, it will move or travel, let us say I am using layman's terms again, it will move or travel in such a way as to again reach equilibrium now, right. So for let us say for your sake of understanding, let us say I am trying to get the system here and you have the ball here, let us say. So let us say the system is at equilibrium now, right. Let us say if I move the ball to the right and release it here, it is again going to try to come back to its equilibrium state, right. Or if I move it to the left and release it here, it is again going to try to come back to its state of equilibrium, more or less that is the principle of Le Chatelier, let us say, right. Again, what is it now? If a system is at equilibrium and it is perturbed in any way such that it is no more at equilibrium, it is going to try to move back, not try to, it will move in such a direction as to reach equilibrium again. So what does that mean now, let us say? So let us say if in this case let us say Q is decreased, right. So decreasing Q, what does that mean now? So you end up adding A and B. So we have A plus B going to C plus D, and say decreasing Q means you in general add more quantities of A and B, right. So what does that mean now? From the Le Chatelier's principle, what does that mean? Let us say it is equivalent to moving the ball to the left here. So earlier it was here and now I added more reactants. So the ball is now here, let us say. It is going to try to move in the forward direction here, or the reaction is going to go through in the forward direction, and that is what you would see here, I guess, right. Again, how do we relate that to the equation that we just described that though? Delta G equal to delta G naught plus RT natural logarithm of Q, right. So as Q decreases, right, you see that I guess the effect is such that the delta G decreases too, yes, meaning that the forward reaction is feasible, yes. Again the inverse of it, what would happen, let us say if you end up increasing the Q though, right, that would mean that if you increase the Q, that more or less translates to delta G increasing too, right. So that makes the reaction infeasible, or it means that the reverse reaction is feasible, right. So that is what we have here. And the next aspect we are going to look at, the term is equilibrium coefficient. So let us say if the system is at equilibrium, right, if the system is at equilibrium, then K will be equal to Q, right, and that is what you want to understand here. So again keep in mind that whenever we are talking about Q or K, we need to define the relevant or the variables are activities and not concentrations, right. So, if a system is at equilibrium, that is when you will have Q, which is the reaction coefficient, being equal to K, the equilibrium coefficient, right. And so, let us see why this is important, or why we need to discuss this in greater detail. So, I believe we will move on to the next slide. So, here we have, or we are trying to develop relationship between K, right, which is the equilibrium coefficient, and delta G of your reaction. Again, what is K, I guess, for reaction mu A. And so, this is the example reaction that we are using in our class. So, what is that equal to again? So, when the system has reached equilibrium, you will have relevant what do we say, activities, right. So, here I will use the different terms. Right, here again we have activities of the products rise to their stoichiometric coefficients divided by activities of the reactants rise to their respective stoichiometric coefficients. So, again, when is this particular set of, or these set of variables equal to equilibrium coefficient, though? When the system is at equilibrium. So, when it is at equilibrium, you will have relevant activities of the various compounds, and that is when you can calculate K. So, here I guess we are trying to develop a reaction, pardon me, relationship between K and delta G, right. So, let us try to write down what we know so far. Delta G equal to delta G naught plus RT natural logarithm of Q, right. So, at equilibrium, what do we know? We know that delta G is equal to 0, right, and we also know that Q is equal to K. Yes. So, plugging the relevant values in, we get 0 equal to delta G naught plus RT natural logarithm of K, or K is equal to exponential minus delta G naught by RT, right. So, what does that mean? So, let us say if you have K, you can calculate delta G naught, or if you have delta G naught, you can calculate K. Again, what is delta G naught, please? Change in Gibbs energy of the system during a reaction at standard conditions. So, you know, once you have the relevant or one variable, you can calculate the other variable, more or less. That is going to be useful to you throughout the course of the class, or in general in your engineered systems too. So, here I guess the second case is we are trying to develop a relationship between K, Q and delta G. So, let us see what we have here. So, I guess here we have delta G equal to delta G naught plus RT natural logarithm of Q, right. So, and we know that delta G naught is equal to minus RT natural logarithm of K, you know, that is from more or less this particular equation here. So, plugging that in, what does that mean? That is equal to minus RT natural logarithm of K plus RT natural logarithm of Q, right. And so, that is equal to, or that translates to delta G equal to RT natural logarithm of Q by K, right. And so, this is a relationship we are going to use widely, right. So, you do not need to mug up anything here, everything is logical here, right. So, these are the take home messages here, and let us look at what we just discussed now, right. So, we were able to calculate K given delta G R naught, or you know vice versa, and again we see that we have relationship between delta G and the ion activity product and equilibrium coefficient. So, what does this mean though? In general, in your standard tables or such, you will have the K values or equilibrium coefficient. K is the capital K here, equilibrium coefficient given for most of the relevant reactions now, right. So, let us say if you know, or if you can calculate the Q at any particular point in time, let us say, right. You know the relevant activities or concentrations, you can calculate Q, right, and then you can end up calculating RT natural logarithm of Q by K, right. And then what will that give you an idea about? It will thus give you an idea about delta G. So, you can calculate, is delta G negative, is delta G positive, or is delta G 0. So, what happens here when Q is greater than K? What does that mean, right? So, I am going to work that out here. So, when Q greater than K, as you look at this relevant reaction, that translates to delta G being positive, right. And when Q is less than K, what does that translate to? It translates to delta G being negative. And obviously when Q is equal to K, what does that mean? It means delta G is equal to 0 or the system is at equilibrium. So in the same case again, so when Q is greater than K, you know that the reaction is infeasible, right. It is infeasible, that is what you see, delta G is positive. So again when Q is less than K, delta G is negative. So the forward reaction is feasible. And again here we have the 3 cases here, right. So when Q greater than K, the forward reaction as we have defined it is infeasible, but the reverse reaction as in C and D going or reacting to form B and A is going to be feasible, right. And when Q less than K, the forward reaction is feasible as in written as A and B reacting to form C and D and so on. When Q is equal to K, obviously that means that the system is at equilibrium or delta G is 0, and then there is no further change in the system, right. So let us try to summarize what we have looked at so far and then wrap it up for this session. So I believe we started talking about the calculation of the relevant aspects or Gibbs energies at non-standard conditions. In the previous classes we talked about how to calculate at standard conditions. And how did we calculate that at the standard conditions? We let us say you have elements 1, 2 reacting to form compound 1. We are defining the Gibbs energy of formation of these particular elements, right. Gibbs energies of formation of these elements. We are setting that those are the references and they are being 0. So from that you can calculate the Gibbs energy of formation of the relevant compounds at the standard conditions, and that is how we went about that. And obviously most of these will be in your standard tables now. So if it is at non-standard conditions, obviously you will need to calculate that. Non-standard conditions, 3 cases, what are they? We look at composition, we look at temperature, we look at pressure. So today we have discussed the issues with respect to composition, especially with respect to reactants, the activity or activity of A not being 1, I guess, right. So we discuss how would the situation or scenario change if the activity of the relevant compounds is not or reactants is not 1. So in the next class we are going to talk about composition of non-reactants and so on. So I guess with that I will bid farewell and thank you.